Now there's a fourth dimension. The fourth dimension is time. Some of the models, even three-dimensional ones, are not time dependent. In other words, they only calculate what the equilibrium climate would be. You make some changes, you recalculate the model, and that tells you if you waited a long time, this is the climate you would end up with. But as I mentioned earlier, there are lag times. For example, lag times between when we put carbon in the atmosphere and when we see the effect of that on climate. And so the most sophisticated models are also time-dependent models, and they calculate as time goes on. They advance in time, doing a big calculation of this entire model, all these cells representing the globe and the atmosphere and the ocean, time and time and time again. And so they give you a picture of how climate changes over time. Those are the most sophisticated of the models. Many of these models, by the way, use specially developed modules for different parts of the model. For example, the oceans may be treated differently in a model that oceanographers have developed from the atmosphere. And what climate modelers do with these large-scale models is take an ocean module, for example, that is known to calculate ocean properties well, and they couple it mathematically, computationally in their computer model at the surface of the ocean where it joins the atmosphere. So the ocean model couples to the atmospheric model, and those are called coupled GCMs, AOGCMs, atmosphere-ocean coupled global climate models, or atmosphere-ocean coupled general circulation models. Now, these models are not perfect. And they're not perfect for a variety of reasons. They're not bad, but they're not perfect. And one of the most important reasons is that their resolution is limited. By resolution, I mean how finely do these models divide the Earth and the ocean and the atmosphere into small regions. And even the best of the global models today have grid cells that are only maybe 100 miles on a side. So maybe a piece of land area 100 miles by 100 miles is what they're representing as one unit. They don't get down to any detail smaller than that. They divide the oceans and atmospheres into maybe 20 to 40 layers. That's pretty good, but it's not perfect because these are really continuously varying regions. Even if you do what we do today, grid cells 100 miles on a side and 20 to 40 layers in the atmosphere and ocean, you've got several million of these grid cells in your model. And each of these grid cells probably has dozens and dozens of equations that have to be calculated to describe the flows of matter and energy and momentum into and out of that grid cell. So you can imagine that you have an enormous computational task. These models, except for the simplest ones like the zero-dimensional model I described earlier, or maybe that two-box model that can be calculated by pencil and paper, all the rest of them, they have to be done on computers. And the global climate models we have today, the biggest ones, tax even the fastest computers we have. And they tax them to the extent that in 24 hours of actual computing runtime, a day of actual runtime, a full day, run a computer running 24 hours, they can advance the climate maybe 5 to 10 years. So if you want to explore what the climate's going to do for 100 years, you may have to run this model for 20 days, for the better part of a month. And if you want to really ask long-term questions about what's going to happen, you may have to run for months and months and months. There are climate model runs that have taken the better part of a year. And this is a big problem. Climate computers, models tax even the fastest computers. Now, there's hope for the future. And that hope lies in Moore's law. If you have seen my teaching company course, Physics in Your Life, when I talk about semiconductor engineering and the development of computers and so on, I talk about Moore's law, which is sort of an empirical statement that says computing power doubles about every 18 months. That's rapid exponential growth, and that's why the personal computer you bought yesterday is already obsolete, because computers are advancing that fast. And so there's hope for the future. Our climate models are improving in resolution and the ability to calculate for long times into the future because of these advances in computer engineering that are bringing us ever faster computers. And that means with faster and faster computers, we can make the resolution finer and finer, and the models become generally more accurate that way. There are other reasons the models aren't perfect. We don't understand the details of every climate process, for example. Some processes that are in there, like, for example, the radiation of infrared energy from a hot surface, we know precisely. We understand the physics of that perfectly. It's based in fundamental physics. But other processes, particularly processes involving clouds, the transfer of energy through clouds, depends on the size of the droplets in the cloud, the condensation nuclei on which those droplets condense, the structure of the cloud, the reflectivity depends on all those things. We really don't understand clouds in all that detail. And clouds and some other processes also have to be sort of put in empirically. We look at what the real world does, we make a kind of empirical equation that reflects that, and we put that in our climate model. So we don't understand all the processes from first principles. It would be great if we could just throw a few laws of physics into a model and say compute the climate, but we're nowhere near there yet. That doesn't mean the climate models aren't valid. It simply means they aren't all based entirely on first principles. Another problem. Some of the processes that we want to describe happen at size scales below that of these grid cells. For example, if you have a city is probably substantially less than 100 miles across. So if you have a 100 by 100 mile grid cell and you want to include the climatic influence of that city, which has the effect of raising the temperatures because of this urban heat effect I talked about earlier, how do you include that? Well, you've somehow got to smear that city out over that whole 100-mile grid cell, for example. A particularly important phenomenon that occurs often at scales smaller than the grid cell size is clouds. Imagine a sort of semi-fair weather day when you've got a bunch of little puffy cumulus clouds. Those are a lot smaller than 100 by 100 mile grid size. Suppose the atmosphere is half covered with these small cumulus clouds. Well, you might say, okay, I can model that in my model by saying the entire grid cell is covered with clouds, but they're only 50% opaque. It sort of achieves the same thing. The same amount of solar energy gets to the ground as it does if half the sky is covered by completely opaque cumulus clouds. But if you think about that a little bit, that's physically rather different. A thin overcast that blocks out half the sunlight is a very different condition than having regions of clear sky with direct sunlight coming through, separated by regions where clouds are completely blocking the sunlight. In fact, you can think of some phenomena that might occur. Sunlight can actually bounce off the vertical sides of those clouds and be scattered downward, and you can actually get regions where the intensity of sunlight is a little higher than it would normally be in clear air because of that effect. Parameterizing the presence of those clouds, and it's called parameterizing, it's called subgrid parameterizing the presence of those clouds by assuming a uniform overcast with the same total amount of sunlight coming through, just doesn't cut it completely. It's a first approximation, but we've got to do better. And so a lot of these climate models include sophisticated so-called subgrid parameterizations that take into account processes that are occurring on spatial scales that are smaller than the grid size. Forests, lakes, those are agricultural regions, are other areas that might have to be handled with subgrid parameterization. One of the most important aspects of the climate system, and one that's incorporated into the models, and we think correctly in most cases, are feedback effects. What is a feedback? Well, here I am teaching a class, and if I asked you to give me some feedback, unfortunately it's not an interactive class, but you can't. I say, hey, give me some feedback on my teaching. You say, hey, Wolfson, you're talking too fast. Well, then I might slow down a little bit and talk a little slower. That's feedback. It's a corrective effect. I ask for some correction, and you give me the correction, and my behavior changes as a result. That's a feedback that is corrective. Some feedbacks are corrective. Other feedbacks exacerbate the original change. Feedback effects are additional effects that either enhance or diminish the effects of some original change. That's a sort of cumbersome way to describe it. If the additional change enhances the original one, that's called a positive feedback. In the climate system, if something makes the climate get warmer, and that causes some additional effect that makes it get warmer still, that's a positive feedback. When I talked about the correlation of carbon dioxide and temperature over the paleoclimate record, over those 400,000-year ice core records, I said there were feedback effects, positive feedback effects. A little more carbon dioxide came into the atmosphere, made it a little warmer. That caused other effects that made more carbon dioxide come in, made it a little warmer. We had a leapfrogging there of positive feedback. On the other hand, if the additional change opposes what was going on at first, then that's called a negative feedback. That's the self-correcting. If I start to talk faster and you scream at me, hey, you're talking way too fast, that's a negative feedback. It corrects, it diminishes the original effect. But as I'll show you in a moment, it doesn't necessarily correct it completely. There are a lot of feedbacks operating in the climate system, many, many feedback effects. They involve all kinds of factors, from biological organisms to physics, to chemistry, to geology. All kinds of feedback effects operate in the climate system. One of the most important is called ice albedo feedback. Albedo is a word that means reflectivity. The Earth's albedo, for example, is about 30%, about 0.3, which means about 30% of the sunlight coming to Earth is reflected back into space. Different parts of the Earth have different albedos. The oceans are dark, they absorb sunlight, they don't reflect much, and they have a relatively low albedo. Ice sheets, snow, are very reflective, they have a very high albedo. The land surface, well, that depends on what it's made of and what the vegetation looks like. Forests have fairly low albedo. They absorb a lot of sunlight. They aren't very reflective. Deserts have a fairly high albedo. They reflect a lot of the incident sunlight.